Good morning, fellas. Today is Wednesday, March the 25th, and today we are going to talk about section 10.4, which is potential energy. Now, um, we've talked about energy in terms of the various kinds before. We talked about kinetic, potential, heat, and so on. But today we're going to concentrate on the idea of potential energy in both gravitational and elastic forms. So, generally speaking, potential energy is simply energy that can be stored, all right, and then readily converted to, and that's the key here, is other forms such as kinetic or thermal or that sort of thing. And we refer to uh, potential energy and energy in those kinds of forms that can store useful energy as conservative forces. And the two examples that we're going to cover today are gravity and elastic forces. All right, both of these forces can store useful energy for us. Now, if those are what we refer to as conservative forces, then forces that do not store useful energy are called non-conservative forces. Think about examples of non-conservative forces as things like friction, which is converted to heat, so thermal energy, as well as kinetic energy is a non-conservative force. It doesn't store energy, it's using energy. So let's start with the idea of gravitational potential energy. Okay, the changes in gravitational potential energy is based on how high you lift an object. All right, an object's mass remains constant, the acceleration of gravity remains constant, but the height of the object above the ground is what gives it gravitational potential energy. And we used this last year a great deal in our honors physics course. So if you start down here at this position, and that's supposed to be an arrow. um, in any event, if the value of y is, come on, can't get this to work. There we go. If we use this as the starting position in terms of, sorry about that, in terms of ground level, so y equals 0 meters, there's no gravitational potential energy stored here at all. All right, the book is lying on the ground, and therefore it's got no gravitational potential energy. If you lift it to a certain point, all right, and we'll call this the real start point. So some height, which we'll call yi, all right, the initial height above the ground, then there's potential energy stored in it. If we then increase that height and lift the book to this point, this gives us a final height and therefore a new gravitational potential energy. And so the difference in potential energy here is going to equal the change in mass times gravity times the height, or what you could say is m times g times delta y. All right, so that's the new potential energy, the change, delta ug, if you will. Okay, so here's the formula. All right, the gravitational potential energy of an object with a mass m at a height y above the ground is equal to m times g times y, assuming that when y equals 0, there's no gravitational potential energy. All right, we can choose whatever reference level we want for this, since only the changes in the gravitational potential energy really matter. So if we look at the hiker here, if the hiker chooses to walk up path A, he goes up to this point, and then again up to the next point, assuming that he has a certain 0 gravitational potential energy here, then at a height of 100 meters, he's going to have 80 kilojoules of gravitational potential energy. Well, then at 200 meters, he's going to have 160 kilojoules of gravitational kinetic energy. Now, the thing that I want you to realize here is that it doesn't matter what path he takes in order to get here. All right, he's going to end up, whether he takes point A or path A or path B, doesn't really matter. He's still going to get to this grand total gravitational potential energy of 160 kilojoules, whether he goes up a step at a time or whether he goes up the whole slope all at once. All right. So because gravity is a conservative force, gravitational potential energy depends not only on the height of the object, only on the height of the object, but not on the path that the object took to get to that height. So if you lift a book straight up in the air, you give it X amount of gravitational potential energy. But if you take that book and you lift it here, and then here, and then here, and then here, and eventually get to the same point, you still have the same amount of gravitational potential energy. All right, the same amount of work has been done to get it to that height, and therefore it has the same amount of gravitational potential energy. Now, in terms of elastic potential energy, the same kinds of things occur here. Only this time, we're not storing energy because of the force of gravity. We're storing it due to the elasticity of the spring. And although the example on this page shows elastic potential energy in terms of the compression of a spring, this is also true when you stretch a spring, because it has the potential to snap back into place, or from here to snap back into place. So elastic or spring potential energy is stored when a force compresses a spring. So in this case, we start with the spring in equilibrium. In other words, relaxed, not pushed in or stretched out. Okay, and so when we then apply a force, and you can see the force vector represented here, to the spring, and we displace it by a distance x. All right, as the more you push on that spring, the more force is going to be required in order to do this. And this relationship is described by a guy by the name of Joe Hook. All right, he was a naval captain, so you can call him Captain Hook if you want. But Hooke's law describes the force required to compress or stretch a spring. And that formula actually is Hooke's law is F equals K times X. Now, X is, of course, the distance that the spring is compressed. This is called the spring constant. All right, the spring constant. And the spring constant, by the way, is different for every spring. It depends on how tightly the coils are wrapped, what the diameter of the coils is, how big the thickness of the wire that is used to make the spring. So a number of different factors go into producing this spring constant. And so every spring potentially has a unique spring constant. All right. So if you then integrate the Hooke's law from the previous, take the derivative rather of Hooke's law, you end up with the formula for elastic or spring potential energy. And this is given as 1/2 kx squared, where again, k is that spring constant for each individual spring, and x is the distance that the spring is stretched or compressed. So the elastic potential energy stored in a spring is determined by the average force that's used to compress the spring from its equilibrium length. And that elastic potential energy of a spring displaced a distance x from equilibrium, assuming that the original potential energy is 0, when the end of the spring is at x equals 0. So example 10.8, pulling back on a bow. All right, well, and if you an archer, if you've ever fired a bow, all right, if you pull back on the string, you are essentially stretching the bowstring. And so an archer pulls back on the string on her bow to a distance of 70 centimeters, all right? You're going to have to convert that to 0.70 meters from its equilibrium position. To hold the string at this position takes a force of 140 newtons. So the question is, how much elastic potential energy is stored in the bow? All right, well, the first thing you're going to have to do here is figure out what the spring constant of the bowstring is. The bowstring is. So a bow is an elastic material, so we'll model it as obeying Hooke's law. So F sub s is going to equal negative kx, where x is the distance the string is pulled back or stretched. We can use the force required to hold the string and the distance it's pulled back to find this bow's spring constant, k. All right, we can then plug that k value into the formula for elastic potential energy. All right, so we have to start with Hooke's law here. So Fs equals negative kx. So we rearrange this algebraically to solve for k. We know that the force is 140 newtons. The value that we stretch the spring, you notice I converted this to meters here, and that's going to give me a value for the spring constant of 200 newtons per meter. I then come down to my elastic potential energy formula, and 1/2 kx squared is going to be equivalent to 1/2 times 200 newtons per meter. Notice the units for k are newtons per meter, times 0.70 meters squared, and that leaves me with 49 joules of elastic potential energy. Now, interestingly enough, if you then release the bowstring, all right, how much kinetic energy does the arrow have? Well, in assuming that no energy is lost as heat or due to friction, which is not really accurate, but let's assume that, then the arrow will now have 49 joules of kinetic energy. Okay, so when the arrow is released, the elastic potential energy will be transformed into the kinetic energy of the arrow. And so 49 joules is a reasonable quantity for the kinetic energy of an arrow. Okay. Gentlemen, your homework for tonight is to do questions 16 to 23, odd numbers only, on the at the end of chapter 4. Have a great day.